today what we are going to learn is a new topic which is about median and order statistics. So first of all, if we talk about the terms in the topic itself, we have two terms. One is median, which is actually a very common term, and I hope you all understand what actually median is. So that's, we can say, it's a middle element when we are kind of arranging, after arrangement of elements of a set, the middle one, arrangement as in like increasing or decreasing arrangement, the middle one is a median. As far as order statistics is concerned, that is something which we need to kind of understand, or which we need to learn. Order statistics, if we go by definition, so we can say that the ith order statistics of a set of n element is the ith smallest element in that set. Now, what are the common examples of this, corresponding to this definition of order statistics is minimum and maximum. So, minimum, if we talk about, is the first order statistics, because that is the minimum element or the first smallest element. And if we talk about maximum, that is the last element, or we can say that that is the nth order statistics. So this is what order statistics is. Ith order statistics means within the set of n elements, ith smallest element in that set. So minimum is first and maximum is nth order statistics. So here we can understand this concept with the help of a visualization which is given on the screen. If we talk about kth order statistics on the similar lines, so it is nothing but the kth smallest element of the array. So here I have given you an array in which this array, now if you can see, is actually in the sorted order. So the first order statistics is 3, which is the minimum element. The nth order statistics, which is 10, of course, here is 75, the 10th order statistics. And if I am talking about, let us say, any other number, kth number in between, so we have 8th order statistics, which is given or which is pointed here in the figure as 54, because this is the 8th smallest element. So now I hope you understand what actually order statistics is. Now, in our today's topic, we are going to understand, or we are going to analyze these two topics. One is median, or these two subtopics I would say rather. One is median and another one is order statistics, and we'll be looking into various algorithms in order to determine, in order to find these medians and nth order statistics, or any order statistics for that matter. If we talk about median, as I have told you, that is the middle element. Now, middle element in case of the number n, which is nothing but the size of the array, if n is odd, the median will be n plus 1 divided by 2 order statistics. So that means the middle element will be the median, and middle element in case of an array whose n is odd will be n plus 1 by 2. So for example, if we have 11 is the size of the array, 11 is our n. So the 6th order statistics will be our median, which is 11 plus 1 divided by 12 divided by 2. So if n is odd, the median is n plus 1 divided by 2 divided by 2th order statistics. Now this was the case when your n is odd. When your n is even, there can be two medians. One is often they often referred to as lower median, another one as kind of higher median. So if n is odd, let us say your the n is even. So if your size of the array is 10, so your element 5 and element 6, or your 5th and 6th elements, both are medians. One is your 5th and 6th order statistics, both are medians. One is the lower median, another one is the higher median. So if n is even, there are two medians, one is n by 2th and another one is n by 2th plus 1 order statistics. So this is what how we can say these median and order statistics, these two subtopics are related. So today we are going to deal with this problem, which is nothing but selecting the ith ranked item from a particular collection. So, if I is equals to 1, our job is very easy. We are looking for the first smallest element. If I is n, I is equals to n, again we are looking for the last smallest, or we can say the biggest element. If I am talking about median, and in case of n is even, this median could be floor of n by 2, or it could be ceiling of n by 2, as I have given you the two specific cases of n equals to odd and n equals to even. So, what actually our problem is? So, first of all, the problem is we need to determine the ith smallest element. This problem is more specifically known as selection problem. And what is the formal problem statement corresponding to this is, given a set A of n distinct numbers and an integer I, where I is ranging between 1 to n. So, 1 is less than equals to I is less than equals to n. What is the goal? The goal is, or what do we need to do? We need to find the element x belonging to this set A, that is ith smallest element. So, within a set or within an array, we have been given an integer I, and we need to find that ith smallest element, as I have given you example with the help of a figure just 2 slides before. Now, what is the goal? This was the formal problem statement. The goal is not just to solve the problem, why I am telling you in a short while. The goal is to develop efficient algorithms to solve this problem. Why I am insisting on the word efficient, that I'll be telling you in some time. Now, what is the initial assumption? Initial assumption is elements are all distinct elements. We have taken this initial assumption for the sake of brevity, for the sake of simplicity, and this obviously can be extended to handle the duplicates. Now, I have just told you that our goal is not just to solve this problem, our goal is to develop efficient algorithms to solve this problem. Because if we just need to solve the problem, the simplest idea could be just sort the array. So, why are we not just sorting the array if we are going for selection problem, and you understand which selection problem I am referring to now. So, sorting approach is we need to sort the given input set or given input array, and that sorting time is going to take order of n log n, or we can say more specifically we can say theta n log n, and this is going to return a of I or a of I minus 1 in case of your array is starting from 0. If your array is starting from 1, if one indexed array is there, then a of I we will be looking for, we will be looking for a of I minus 1 if it is 0 indexed array. So, if my array is sorted, or let us sort the array in n log n time, then reporting that particular a of I will not take more than a constant amount of time, which is order 1 time. So, total which is the sum of these two approaches, these two steps, one is to sort the input array, another one is to return or to report a of I, is certainly not going to take any time, is not going to take order n log n. I mean, this is the standard time which we generally consider for sorting the array, although there are algorithms which may take n square in worst case, or they may take order of n in the best case, but generally we talk about n log n is the kind of time which is there to sort the array. So, the trivial way to selection problem is to sort the entire array. Now, please make it very clear, or please notice that this is one trivial or one naive way to solve the selection problem. This is not the best, or this is not the efficient way to solve the selection problem, and that is why I was telling that the goal is to develop efficient algorithms for this problem. So, here we can if we go by selection via sorting, we can apply any sorting algorithm which is reasonable to give us n log n time. It could be heap sort, it could be your merge sort, and then we are returning that particular a of I or a of k, whatever you can say. Now, this is going to take theta and log n time, and here we face a question which is a question which haunts algorithm designers every time, and the question is, can we do better than this? So, yes, if we talk about the selection problem, see the idea of the selection problem is to pick one particular element, or what is the output which is being expected by the selection problem is one particular element. There is no need to sort the entire array. If we can do if we can have an algorithm which is performing in less time as compared to the sorting algorithm, because sorting is not the goal. The goal is to pick that ith order statistics. So, ultimately sorting is not going to is not the best way to do this. Now, let us say we assume we have an unordered collection. If the collection is already ordered, then our job is actually done. It is just an order one time, which is just reporting is the task which is remaining, and the problem becomes trivial. So, I am assuming here that the collection is unordered, and within this unordered collection we need to find the ith order statistics of this the collection A, which is nothing but A of I. So, we can sort the list first, as I was just discussing, and we will be having theta and log n. But the question was, can we do better than this? Certainly yes, we can do better, and we can solve this problem in theta n. So, let us try to explore the problem. We have seen three examples of this ith order statistics. One is to find the maximum, another one is to find the minimum, and next was to find ith order statistics. So, we can find maximum and minimum in theta n time. Now, this is very obvious. How we are going to do that? We will be looking into some trivial naive algorithms for this as well. Question comes up with this third case, which says, can we find any order statistics in linear time? Yes, we can do that, but it is, although it is not very obvious, or we do not have any till this point we have not seen any algorithm in regarding to this. So, if we need only one specific order statistics, the goal is not to sort the entire array. So, yes, we can do better than this, and we can achieve this in order n time. Now, there can be various ways. If we go by the way of sorting, we can apply some non-comparison based sorting algorithms. What are those non-comparison based sorting algorithms? Which are radix sort, which are bucket sort, which are count sort, and we have seen these in our series of algorithms as well. So, if sorting of entire array can be done using some non-comparison based sorting algorithm, and the non-comparison based sorting algorithm which I just named as count sort, radix sort, and the bucket sort, these are actually linear time algorithms. So, we end up with order n, the whole time is order n. But these non-comparison based sorting algorithms comes with so many constraints, as in count sort put up a different kind of constraints on the input set. So, is your bucket sort is applying some different constraints. So, your input set is not free. So, with these constraints we cannot operate, or we cannot ensure that your input set is going to be kind of bounded by these constraints. So, non-comparison based sorting algorithm, or we can say usage of non-comparison based sorting algorithm is is the idea which I am ruling out here. But still apart from or beyond using this non-comparison based sorting algorithm, we can still achieve our order n time for ith order statistics. So, again ith order statistics, 3 cases: minimum, maximum and ith order. So, let us see, finding minimum element, if you recall, is actually a trivial problem in case of algorithms. So, what do we need to do? We actually, if we look into the algorithm, is we need to iterate through the array and we need to keep the track of the smallest element encountered so far. So, let us say we have an algorithm minimum and an array which is A, and presently I have taken the first element as the array and I am assuming that my A is 1 index, it is not the 0 indexed. We can configure or we can customize this, we can tweak this algorithm to take care of 0 indexed also. So, minimum value presently is A of 1, and then starting from I is equals to 2 to A dot length, if we encounter any A of I which is less than minimum value, we will be updating that minimum value with the new minimum which is A of I, and finally we will be returning minimum value. So, for example, we have 2, 1 and 3, and 2 is the present minimum, the first value. When we compare it with 1, we will update our minimum value as 1, and we keep on iterating this through the whole array. So, finding minimum element, we have a very standard naive algorithm for this, which is iterates through the array and keep track of the smallest element encountered so far. What about complexity? Analysis is very simple, and it is a very straight kind of an algorithm, exactly n minus 1 comparisons, because first element we are taking as minimum and we are comparing it with other n minus 1 elements, and time complexity order of n. So, for exactly n minus 1 comparison, it is order n. So, finding first order statistics is trivial, and we all know that can be done in order n. Finding the ith order statistics, which is the maximum element, is a problem which runs parallelly. Now, this is also symmetric to finding the minimum. We will iterate through the array and track the largest element, and here we are kind of keeping the track of largest element instead of keeping the track of minimum element. So, maximum element says, again for an 1 indexed array, max value is equals to A of 1. Then we start iterating through array, which is I of I is equals to 2 to A dot length. If A of I is greater than Maxwell, then Maxwell is equals to A of I, and finally we will be returning this maximum value. So, now this is also trivial. Coming to the analysis, exactly the same, which is n minus 1 comparison, time complexity order n. So, out of 3 cases of ith order statistics, we have taken or we have sorted the sentinel cases, one which is related to first order statistics, another one which is related to nth order statistics. Now, taking this first order and nth order statistics only, I am still yet to cover the ith order statistics. Can we do better than this? Again the same question. We can find, if we need to find minimum and maximum simultaneously, what is going to be the naive approach for this? So, problem for both finding minimum and maximum elements in a single pass, that is what our problem is. So, we need to find both minimum and maximum elements of an array in a single path. So, naive method says call this minimum which we just explored, n minus 1 comparison for that, call maximum, again we just explored, n minus 1 comparisons for that. So, in totality it is going to give 2 n minus 1 comparison, which is 2 multiplied by n minus 1 comparison. So, n minus 1 comparisons for minimum, n minus 1 comparisons for maximum. So, twice of n minus 1 comparison. Time complexity is still order n, but if you see into this in details, it is with a higher constant factor. So, even if we talk about simultaneous minimum and maximum, we end up with order n only. Do we have any optimized version of this simultaneous minimum and maximum? Yes, we can have an improved algorithm, and within this improved algorithm, what we will be doing, that we will be processing the elements in pairs. We will be initializing two values, one is minimum value, another one is maximum value, and what will be the initial values? The initial values will be first two element, or we can say the first element if n is odd. That means the first element will be the min val as well as the max val if your n is odd, or we can have the first element as min val and the second element as max val. For the remaining elements, we will be taking them in pair. Compare the two elements in the pair. So, for example, our n is assuming that n is odd. So, first element is being initialized or being given the value to min val and max val. Now, second number element and third number element we are comparing them, and a smaller one is being compared with min val and larger one is compared with max val. So, first comparison between the elements in the pair, a smaller one goes to min val, the larger one goes to max val for comparison. So, for every two elements we have given three comparisons, and if we analyze this kind of or we can say simultaneous minimum and maximum algorithm, which is the improved or the optimized version, we can say that if n is even, this is going to have 3 into n by 2, which is 3n by 2 comparisons, and if your n is odd, this will have 3 into n minus 1 by 2 plus 0 comparisons, which comes to, after a simple calculation of 2 steps, which comes to 3n minus 3 by 2 comparisons plus 1 comparison initial for n is equals to 1. So, approximately we can say 3 n by 2 comparisons for this. So, if n is equals to 10, so we have 15 comparisons as compared to 18 which is in the naive method. So, improved version is going to give us 15 comparisons. Time complexity, again we end up with order n, but with a reduced constant factor. The constant factor here is reduced because number of comparisons is being reduced from 18 to 15 in case of n is equals to 10, but the time complexity which we are ending with is certainly order n. Now, from here onwards we will move to our second section of this topic, which is nothing but selection in expected linear time. So, here in this lecture what we have covered, so we have covered what we first of all we try to understood the topic itself, which is median and order statistics. We looked into what actually order statistics is, and then we have seen a trivial algorithm for first order statistics, that is minimum, for the last order nth order statistics, which is minimum. Now, what are we left with, or what are we going to cover in our next lecture is about nth order statistics. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.